two-dimensional Taiwan Normal University. It is my great pleasure to be here and share with you some of the work we have been doing and also some ideas we have for the two-dimensional material. And today I'm going to talk about the optical properties of two-dimensional materials. For the past 20 years, I look at the periodical table every day, really every day. In the early days, we studied the optical properties of the carbon-based materials, including graphite, diamond, and carbon nanotube. And recently, graphene, a very thin layer of graphite, has attracted a lot of attention because graphene is the mother of all the other carbon-based materials, including graphite, carbon nanotube, and C60 buckyballs. And graphene also shows a variety of interesting electrical and optical properties and potential practical applications. We study the optical properties of graphene, and also we extend the measurement to the flex phosphorus, as well as the transition metal dichrogenide material, such as moly disulfide, moly diselenide, tungsten disulfide, tungsten diselenide, and so on. And people are interested in these materials because they are exceptional materials with a lot of interesting properties and practical applications. For example, graphene. We know the charge carriers, the electrons in graphene, are extremely mobile, very mobile, and it could allow the graphene transistor to process the data at very high rate. Some devices have already clocked in at more than 400 gigahertz, many times faster than the silicon devices. However, graphene does not have a band gap. It's a zero band gap, making it very hard to turn the current off once it starts flowing. And this is a big problem for the logic operation. You have 1 and 0, okay? This is a problem for the graphene application. So the researchers are trying to soak the graphene with the different elements and try to open a small band gap. However, this also slows down the flow of the charge carrier. By contrast, another two-dimensional material, boron nitride, is an insulator with a very large energy band gap energy, approximately 60 electron volts. It's an insulator just as like the glass. And also I mentioned in the previous transparency the transition metal dichrogenide materials, and depending on the selection of the different elements, moly, tungsten, titanium, and sulfide, selenide, and these materials also show a variety of interesting electrical and optical properties. And very recently, people are interested in the flex phosphorus, BP, because of its combining high carrier mobility and with a fundamental band gap. It shows a lot of applications. And researchers are promising a lot of applications for these two-dimensional materials, from fast computer chips and your flexible touch screen to solar cells. However, and so far there have been found only few practical uses. why is so difficult to take advantage of the amazing property of the two-dimensional material to make the application? One is the biggest challenge for the two-dimensional material is to find the economical and reliable way to make high quality two-dimensional material for industry scale production. At this moment, the best way to make the high quality two-dimensional material relies on the chemical vapor deposition. However, this chemical vapor deposition product usually include a lot of defects, disorders, and grain boundary, impairing the electrical and optical properties of the two-dimensional material. So we need the young grad students to join this project to think about the possibility of the breakthrough, to think about the new way to make the high quality two-dimensional materials for industry scale production. So this is a very good opportunity for this young grad students. And secondly, research now are trying to tune the electrical and optical properties of these two-dimensional materials by combining graphene and the other two-dimensional materials layer by layer. Okay, very interesting topic. And this research we call van der Waals hyperstructure. Is the hardest topic in the condensed matter physics and material science. For my research group, we are cooperating with chemistry. So I'm from Department of Physics, but we collaborate with the chemists and the material scientists to prepare different kinds of interesting two-dimensional materials. It is very easy for doing a science study in Taipei because Taipei is a small city compared to Jakarta. Also, in the Taipei city, we have three big public universities, including National Taiwan University, National Taiwan Normal University, and National Taiwan University of Science and Technology. So three universities this year become a single university system. Okay, so we are all strongly cooperating each other and making a good research. And first, I'd like to introduce we prepared the graphene sample with molecular decoration. As I just mentioned, researchers are trying to soak the graphene and open a small band gap because graphene does not have a band gap. It's a big problem for the 0 and 1 logic operations. And usually, there are two ways of chemical dope graphene. So one is the substitutional doping. You put the nitrogen or boron atom into the graphene lattice. And the other way is the simple, is the absorption of the molecule on top of the graphene surface. And our experimental is very simple, as you can see. We first put the chemical vapor deposition graphene in this vessel, and then we took the organic molecule of trienzyme, or in another vessel. Trienzyme molecule is an electron-rich molecule, and due to its incorporation of nitrogen atom in the ring, so we are expecting some electrons will transfer from the trienzyme molecule on top of graphene. And we first sealed the two vessels and separated pumps to the vacuum for 30 minutes to remove the air in the vessel. And then put all the setup into the oven and heat it up at 150 degrees Celsius. The evaporation time was approximately 8 hours. And then you will see these triangle molecule will transfer to the graphene surface and making the doping property of the graphene. Here I'm showing you the atomic force microscopy AFM image. This is the AFM image and the cross-section profile of the height of the graphene and the molecular decoration on top of the graphene. So you see the graphene thickness is around 1 nanometer. So this is about 2 layers to 3 layers graphene. And on top of the graphene, there's a triangle molecule. Its thickness about 1.25 nanometers. And second, we also prepare another interesting graphene sample. Graphite nanoplanet. We took this nature graphite with an average size about 500 micron, and then we intercalated this nature graphite with sulfur and nitric acid, and filtered with the distilled water, and then heated up by the thermal shock to different temperatures, 200 degrees C, 400 degrees C, 800 degrees C, in a nitrogen gas for 2 minutes. So as a result, you see this nature graphite is expanding along the C direction. So the volume increases as a function of the temperature. And this exfoliated graphite was then dispersed into the acetone and followed by the best solidification for 24 hours, and we break it apart, and you will get this tiny graphite nanoplanet material. The AFM image shows that each nanoplate has dimensions around 500 nanometers. So the starting material, the dimension is 500 micrometers. Now we down to the 500 nanometers. And the thickness of this nanoplate is around 1.4 nanometer. 1.4 nanometer. So we estimate about 4 layers of graphene. And by changing the temperature to higher temperature, 1000 degrees C and 1200 degrees C, we are able to make a different thickness of the nanoplanet. We can make 3 layers graphene and 2 layers graphene and single layers graphene. So this is another material we prepare for the optical measurement. So this is the first part of my story. We prepare different kinds of interesting two-dimensional material, and next we are going to study their optical properties. And for their optical properties, we are particularly interested in the electronic band structure of the two-dimensional material. So if you open up the solid state physics textbook and do the band structure calculation for the typical electronic material such as gold, silver, and aluminum, and the band structure will show you the energy of the electron is proportional to the momentum square over 2n, and is the effective mass of the electron. So you have this quadratic dispersion band, okay, conduction band or valence band is quadratic behavior. However, if you do the same calculation, electronic band calculation for the graphene, you get this conduction band and valence band is a linear behavior. Now the energy of the electron is linearly with the momentum. We call this electron Dirac quasi-particle. And the conduction band and valence band are Dirac cones. And ideally, if you don't have any doping, the Fermi energy is right here at the Dirac point. Experimentally, how can we confirm this linear dispersion relation of the conduction band and the valence band? And the first way to find out is doing the angle result of photoemission experiments. The angle result of photoemission experiments are based on the photoelectric effect, which was discovered by Hertz, the German physicist, in 1887. And his idea is when the incident photon energy is higher than the work function of the material, the top several layers of the material of the electron will be peeking out of the material. And by looking at the energy and momentum of this photoelectron using the energy analyzer, we can get the information of the electronic band structure of the solid state material. And this is the angle result photoemission measurement of the graphene. Indeed, researchers see this conduction band and valence band are linear behavior. And the second way to identify this conduction and valence band with the linear dispersion is doing the magneto-optical measurement. So if we look at the general physics textbook, we all know in the presence of the magnetic field B, the electron will try to complete a circle, will do the circular motion in the magnetic field B. There will be a cyclotron resonance frequency. For the typical gold, aluminum, silver, metal, the cyclotron frequency is proportional to the magnetic field B. But however, for the graphene, the cyclotron resonance frequency is proportional to the square root of the magnetic field B. It's different from the gold, silver, and aluminum. And the optical techniques I'm using is a terahertz spectroscopy. And terahertz is a very interesting frequency range. Below the 0.1 terahertz, that's 100 gigahertz. We have very well developed technology, very mature electronic devices and silicon devices. When you go above 100 terahertz, we also have a very mature technology. That's photonics, like laser and LED. And we have very good technology on both sides, but not here. We call this terahertz frequency is a technology gap. A little more fundamentally, the terahertz frequency is also an interesting transition region. This is where the classical wave becomes a quantum mechanical photon. This is also the transition region for the electrical transport phenomena to the optical transition phenomena. And furthermore, there's a lot of interesting scientific issues in terahertz frequency. There are many low energy excitation in condensed matter in the terahertz. For example, phonon, plasmon, magnon, and superconducting gas usually occurs in the terahertz frequency. You can also look at the dynamic behavior in terahertz frequency, because the carrier scaling and the recombination phenomena in solid state typically occur on the picosecond time scale. Picosecond. Think about 1 picosecond is the inverse 1 terahertz. So this dynamic behavior occurs 1 picosecond. So terahertz frequency, you can look at the dynamic behavior in the solid state physics. And we are doing the terahertz frequency using the synchrotron light source instead of the laser. We have a very strong collaboration with the synchrotron light source research center either in the United States or in Taiwan. So my student and I, we travel to the synchrotron light center, use the synchrotron light, very bright source, and to the experiment, optical experiment. And also we have very strong collaboration with the University of Tokyo. We cooperating with Professor Takeyama and try to apply the very, very high magnetic field. I just say, if you apply the field, the carrier will try to make a circle. There's a cyclotron resonance frequency. So we use the ultra high pulse field. Okay, we generate the magnetic field easily 50 Tesla, 100 Tesla, 200 Tesla, and even 1,000 Tesla, the world record in University of Tokyo. So that's my happy student working there. Okay, so by using the synchrotron light source and the very high magnetic field, we can find the new optical properties of the two-dimensional material. And just show you one example. This is the we shine the light through our 4 layers of graphene and also apply the high field. This data show the transmission ratio in the magnetic field to 0 field and the temperature at liquid heating temperature 4.2 Kelvin and the magnetic field from 1 Tesla to 17.5 Tesla. There are 2 interesting features I'd like to draw your attention. At first, you see this transmission dip. This dip corresponding to the cyclotron resonance absorption. And secondly, you will see this cyclotron resonance absorption is shifting with the magnetic field B, and also the intensity is increasing with applied magnetic field B. And if we apply the peak position as a function of magnetic field, okay, this is frequency as a function of magnetic field, and we find the cyclotron resonance frequency is proportional to the B, okay, these three peaks, and also we find the cyclotron resonance frequency is proportional to the square root of the B, okay. So they'll tell us in the 4 layers graphene we have normal electron and the Dirac electron coexisting in the 4 layers of graphene. So this is one example I want to show you, the second part of my story. And the third part of my story is we are also looking ahead another interesting optical property of two-dimensional material. We combine the two-dimensional materials and the gold nanostructure. And we first fabricate the gold nanodisk array. So you see the average diameter of the gold disk is around 140 nanometer, and the separation around 45 nanometer. And then we put the two-dimensional material, molybdenum on top of the gold nanodisk, the optical microscope image, and we shine the light through this hybrid nanostructure. Okay, you can see for the gold nanostructure, there's absorption peak around 725 nanometer, but if we put another two-dimensional material on top of gold, the peak shifts to the 750 nanometer. this redshift is due to the increase of the optical index of molybdenite surrounding of the gold nanostructure. And by tuning the gold size and the separation, we find this absorption peak become two peaks, like a camel, like two peaks. Original has a single peak. If we change the size of the gold nanoparticle, gold disk and the separation, we see the two peaks here, and we attribute this interesting behavior is the resonant interaction between the surface plasma and the gold disk and the external of the molybdenite. It's a very interesting research topic recently, surface plasma. And to summarize my talk, and first, this linear dispersion relation of the conduction and valence band in graphene leads to a very interesting optical property. And second, the possibility for manipulating and generating novel optical property based on this hybrid two-dimensional and plasmonic system. And I'd like to acknowledge my good students, Mr. Shen and Mr. Ye and Mr. Chen, and also my collaborators from all over the world, Professor Lee from King Abu Dhabi University of Science and Technology, and Professor Zhou from NTU, and Professor Carr from the United States National Synchrotron Light Source, and Professor Takeyama from University of Tokyo, and Professor Malay in the French University of Turin. So before I close my talk, I'd like to introduce you the National Taiwan Normal University. Okay.
Taiwan, j'ai suivi le chinois à NTNU. Ici, c'est génial.
Hola, estudio en NTNU. Es una buena experiencia.
Night market in Taipei, most delicious food in Taipei. Night market.
Taiwan University 越来是和了200。
studying at NTNU. Looking forward to seeing you.
After watching us the movie, I'm also in the movie. Too hurry. Okay. Just 3 minutes to give a brief introduction to of NTNU. The NTNU was founded in 1946. This year just celebrated 70 years old. So in the past, our single mission is to educate the junior high and high school teachers. Okay, so that we call the normal university. The other universities in Taiwan are abnormal. We are the only normal university in Taiwan. However, in the 1994, we transferred to the comprehensive university. It's like a UI. So we now have 9 colleges, 45 departments.
Becoming abnormal.
Now become abnormal university. So we are thinking take out the normal. And the faculty member includes 1,700 with 3 Nobel Prize winner, and the student faculty ratio 18:1. We have 300 sister universities, and we are going to sign the UI and the NTNU MOU in the university level. So we become sister university.
Brother.
And the most famous in our campus is the Mandarin Training Center. Okay, we offer the foreign students 3-month-long language courses for all levels, and also a variety of Chinese culture and curriculum. If you are interested in studying the Chinese, that is the best place in Taiwan. So for my department, I'm coming from a physics department. This is the number of faculty as a function of their age. So above 60 years old, we have 3 professors, and young professor 3 young professors. So the average years in our department is around 49. It's very young, right? Very young department. That including 15 full professor and 7 associate professor and 7 assistant professor. So we are very young and energetic department in Taiwan, 49 years old. And our student body for undergrad students, around 300 undergrad students, and 77 master's degree students, and 30 PhD students. We have 2 Indonesia PhD students. One is Krishna, he graduated from UI. Krishna, okay, she studied the high energy and particle physics, and she did an excellent research work in our department. She will going to graduate next year with her PhD degree. And the other Indian student is Anis, okay. And we also have 2 Philippine PhD students and 2 Vietnam PhD students. one Indian PhD student, and one Japan master's degree student. So we are trying to recruit international students as many as possible. Okay, because our teaching courses, okay, for master degree and the length of study for master 24 credits, and all the courses are taught in English, and doctor degree, the length of study is 8 semesters, so 4 years, and 18 credits are required, and also all the courses are taught in English. We focus on the 4 main research topics. One is quantum matter, material physics. Okay, there are 14 faculties involved in this big, large areas. We did the research work, nanotechnology, green material science, electronic and semiconductor device, and so on. The other second one is high energy and particle physics. Krishna is joined this group. 8 faculties, 7 faculties, okay, in this research group. They study the particle physics, field theory, string theory, and cosmology. And third one is a newly developed is soft matter and biophysics. Only 4 new faculties in this area. They study nano and biomechanics, nano confined group, and super resolution microscopy for single cell. The final research is we are doing physics education. Okay, our physics education group has 4 faculties. So they do the innovation in the teaching physics pedagogy. For example, a flipped classroom and social learning platform. They also train the international physics Olympic team, and I believe next year will be take place in Indonesia for the international physics Olympic Games. Okay. Right. IFO. And also they train the international young physics tournament physics World Cup for the high school students. They win the gold, the silver, and the bronze medal. And the scope of the cooperation between the UI and the NTNU, there are 2 possibilities. I would like to invite the UI students and faculty to visit our department for 1 week, or 2 weeks, or 1 month, or 2 months for the joint research activity. Joint research activity, and for the publication, we can work together and taking the data and publish the data, publish the paper together. So we will cover the student accommodation fee and the food expenses in the cafeteria for during your visit, and you only need to pay your airfare by yourself. The second cooperation is I invite the UI student enter the master's degree and the PhD program, just like Krishna in our department with a fully funded scholarship. For a master's degree student, we offer the 2-year fully funded scholarship. For a PhD student, we offer the 4 years of fully funded scholarship. And I'm really looking forward to see all of you in our department. Thank you very much.
Thank you very much, Professor Hsiang-Lin Liu. Very interesting presentation and very kind offering from your institution. Thank you. And now we are open for the questions.
we prepared a superconducting thin film sample and shine the singleton light source through the superconducting thin film. If open the superconducting gap, the light will be absorbed. You won't see any transmission. That's the one indication of the superconducting gap. And also you can vary the temperature dependence. So above the superconducting precision, all the light transmitted through the superconducting material. But below the superconducting precision, some of the light will be absorbed. This is the most easy way to find the superconducting gap by using the singleton light source. Thank you for your question.
Okay, for the second question. Okay, thanks for the nice call. Well, actually, I have maybe two questions. The general one. I'm not familiar with the article. But I'm just curious, like, because from what I've read, like, you should place the sample for the experiment, and then, like, what does have, like, when you're doing, like, experiment in routine, like, does it affect, like, the number of layers that you, like, once you place the sample, you set it to reduce the number of layers, right? And does it have, like, impact on the measurement, like
the linear dispersion relation conducting that.
Yeah, and then like and oh yeah, for the second one, like it's because I'm like more familiar with the rare earth speed, and I read like some of the artists experiments on the rare earth speed, and they usually like include like to reproduce the dispersion, so include like the view common with the diffraction from the DS. And we have to do that to reproduce the dispersion of like any
Thank you very much for your two excellent questions. The first one is, you are right. When we do the angle result formulation, we need a very clean surface. So people are clean the surface. But the graphene only one atomic layer of the carbon. How can we clean the surface in the ultra high vacuum? So the way we did, we prepared the graphene sample in the ultra high vacuum and transfer to the chamber, okay, without any treatment of the surface. This is an easy way. And the second question is for the graphene, we don't need to consider the U repulsing energy or hopping energy. It's naturally you see this linear dispersion relation of the conduction and valence band from the same structure to relation. Thank you very much.
Okay, is there any other questions? Okay, I think the time is up. Thank you very much for Hsiang-Lin Liu. Then give you